So now that we have our definition of implication sectioned off over here, let's look at another example of logical equivalence. We've already seen one. Let's go ahead and take a look at another one. So for this example of logical equivalence, let's go ahead and let R be the compound expression, not P or Q. And let's let S be the compound expression, not P and not Q. So notice this R and this S, they are compound expressions. If we want to figure out if these are logically equivalent, we have to figure out if they have the same truth tables, i.e. they take on the same truth values no matter what the values of their underlying variables are. And you notice that the underlying variables here are P and Q. So when we write out our truth table to figure out if these two are logically equivalent, we're going to have to be looking at all the possible truth values of P and Q. So let's go ahead and do that. So if you've really absorbed all of our logical operators so far, that is the and, the not, the or, and the zor, you might be able to fill in this truth table right as is. But personally, I find it a little bit easier if we do a little bit of scratch work on the side. So right here, I'm going to go ahead and section off and do a little bit of scratch work. So this scratch work is going to look as follows. So I'm going to look at every single row right here. So first off, in this row, P is true and Q is true. So let's concentrate on this very first expression right here, not P or Q. Well, in this row, P is true and Q is true. So I could go ahead and substitute this, and this would be not true or true. And if you remember how true is defined, if either one of these is true, then the whole thing is true. So in this case, this thing is going to be not, and that interior expression right here is true. And then we remember that this not sign right here simply just flips it. So this becomes a false. So I know in this particular column right here, all I need to do is put a false on the inside. And for this last column right here, I have not, and I'm looking at the first row, so it's a not true, and not, and then Q here is also true. And I recall that each one of these nots flip things, so this will be a false and false. And if you remember the definition of and right here, this thing is definitely false. So I can go ahead and fill in this entry of my truth table, and I get a false. And I can continue on and fill out this truth table using my scratch work on the side. So again, in my second row right here, P is true. So this thing is going to become Q is false. True or false. By definition of the or, this thing is going to be true. So it's a not true, and it becomes false. So I know in this entry right here, I can go ahead and stick a false. And then for the second one, P is true. So I have a not P, and Q is false right here. So the true, well, it gets flipped by the not right here, so it becomes a false. And this false becomes flipped because of that not. And false and true is also definitely false. And continuing on that fashion, we get the following. So doing out the scratch work, false or true. That's going to be not true is false. Here, P is false, not false, and not true. True and false. That is also false. So this thing becomes false here and becomes false here. And in our last row right here, we have P is false and Q is false. So we're going to get not false or false. False or false, that's false. And then the not flips it to a true. So that means in this column, I get a true. And for this last column right here, I'm going to get a not. P in this case is false. And not. Q in this case is false. So the nots flip it. So it's going to become true and true. Hey, true and true is true. So in this case, we get a true right here. So notice, critically importantly, both falses, both falses, both falses, both trues right here. This part of the truth table and this part of the truth table are completely identical. And because of that, we say, therefore, R is logically equivalent to S. Or expanding it out a little bit, i.e., not P or Q is logically equivalent to not P and not Q right here. By definition of logical equivalence, they have the same truth table. Yes, indeed, they have the same truth table, no matter what the values of their underlying variables are. Therefore, these couple of compound logical propositions are logically equivalent. So great, that's fantastic. We now understand the principle of logical equivalence. But I thought we were talking about implication. What does logical equivalence have to do with implication? Well, remember the motivation for my introducing logical equivalence, because it turns out that implication actually is logically equivalent to a compound expression using logical operators that we have already introduced. And so that is what we're going to look at next, how implication can be related back to ands, nots, and ors.